Welcome to our journey through the cosmos. Today, we embark on an exploration of two captivating concepts, redshift and blueshift. These phenomena not only reveal the motion of celestial objects, but also unlock secrets about the very nature of our universe. Imagine each star and galaxy as a distant traveler, carrying stories in their light. As we delve into redshift and blueshift, we'll discover how the light from these cosmic travelers serves as a powerful tool for astronomers, providing insights into their movements, distances, and even the history of the universe itself. Get ready for an enlightening journey through space and time as we unravel the mysteries behind the colors of light and the secrets they hold. To understand redshift and blueshift, we first need to grasp the fundamental nature of light. Light travels in waves, and these waves can vary significantly in their frequency and wavelength. Imagine light as a vast ocean of waves, each wave a different color, ranging from the warm reds to the cool blues. Light behaves like a rainbow, with each color representing a different wavelength. When we observe light from celestial objects, we measure these wavelengths to learn about their properties, such as temperature, composition, and motion. When we speak of wavelengths, we are referring to the distance between successive peaks of a light wave. Shorter wavelengths correspond to higher frequencies, appearing blue, while longer wavelengths correspond to lower frequencies, appearing red. This spectrum of light forms the basis of our key concepts, redshift and blueshift. Let's begin with redshift. Picture a star or galaxy receding into the vastness of space. As it moves away from us, the light it emits stretches, akin to pulling a rubber band. This stretching shifts the light towards the red end of the spectrum, a phenomenon we call redshift. To visualize this, think about the Doppler effect, which is most commonly associated with sound. Imagine an ambulance racing past you with its siren blaring. As it approaches, the pitch of the sound is high, but as it passes and moves away, the pitch drops. Similarly, the light from a receding star or galaxy is stretched, leading to a longer wavelength and a redder appearance. Astronomers measure redshift using spectrographs, powerful instruments that capture the light from distant objects and break it down into its component colors. This allows them to see the spectrum of light emitted by stars and galaxies. The amount of redshift is quantified as a dimensionless number, often represented by the letter Z. A higher value of Z indicates a greater redshift, meaning the object is moving away from us at an accelerated rate. This measurement is more than just a statistic. It has profound implications for our understanding of the universe. The greater the redshift, the faster the object is receding, providing crucial evidence for the expanding universe. This expansion indicates that the universe is not static. It is dynamic and ever-changing. Imagine being able to look back in time. Redshift allows us to do just that. By studying the light from distant galaxies, we can piece together a timeline of the universe's expansion and evolution. It's like reading a history book written in the language of light, where each chapter reveals a different era in the cosmos. Now, let's turn our attention to blueshift. This phenomenon occurs when a celestial object moves toward us, causing its light waves to compress. Picture this as a train speeding towards you. The sound of the whistle grows higher in pitch as it approaches. In a similar manner, as a star or galaxy moves closer, its light waves are squeezed together, shifting towards the blue end of the spectrum. When astronomers detect blueshift, they understand that the object is moving closer. This information is invaluable for studying the dynamics of celestial bodies. By measuring the amount of blueshift, scientists can determine how quickly an object is approaching. This can reveal important gravitational interactions between stars and galaxies, illuminating the intricate ballet of the cosmos. Some galaxies, such as the Andromeda Galaxy, are moving towards our Milky Way and exhibit blue shift. This gravitational interaction hints at a cosmic dance where galaxies can collide, merge, and reshape the structure of the universe over time. These events are not merely spectacular. They play a vital role in galaxy formation and evolution. So, why are redshift and blueshift so significant? These shifts are foundational to our understanding of cosmic expansion. Observations show that most distant galaxies are redshifted, indicating they are moving away from us. This leads to a profound realization. The universe itself is expanding. Hubble's law beautifully illustrates this relationship. It reveals that the farther a galaxy is from us, the faster it is receding. This groundbreaking discovery has transformed our understanding of cosmology, providing compelling evidence for the Big Bang Theory, which posits that the universe began as a singular, immensely hot and dense point and has been expanding ever since. This expansion raises even bigger questions about the fate of the universe. Will it continue to expand forever, slowing down, or will gravitational forces eventually lead to a cosmic collapse? Will we witness a big crunch, where the universe contracts back into a singularity? These tantalizing questions fuel ongoing research and debates among scientists and cosmologists. Astronomers harness the power of redshift and blueshift in a multitude of ways. These measurements not only reveal the movement of stars and galaxies, but also allow scientists to analyze the very composition of these celestial bodies. When light from a star passes through its atmosphere, certain wavelengths are absorbed by elements present there. By studying these absorption lines, dark lines in the spectrum, astronomers can determine what elements make up distant stars, their temperatures, and even their ages. This information is crucial for constructing models of stellar evolution and understanding the life cycle of galaxies. For instance, by analyzing the redshift of light from distant supernovae, astronomers have gained insights into the rate of expansion of the universe, leading to the revolutionary discovery of dark energy, a mysterious force that appears to be accelerating that expansion. Dark energy is one of the greatest enigmas of modern astrophysics, and understanding it is paramount for unraveling the ultimate fate of the universe. By studying redshift and the distribution of galaxies, scientists are piecing together clues that may one day help us comprehend this perplexing force. Beyond the scientific implications, redshift and blueshift connect us to the universe on a deeply personal level. They remind us of our place in the cosmos and our shared curiosity about the stars. As we look up at the night sky, we are not merely gazing at distant points of light. We are witnessing the ongoing story of the universe, an unfolding narrative of birth, evolution, and perhaps even the eventual demise of stars and galaxies. These concepts inspire generations of scientists, dreamers, and explorers. They encourage us to ask questions, seek answers, and push the boundaries of our understanding. Through observatories, space missions, and advancements in technology, we have the tools to unlock the mysteries of the universe. Each discovery brings us one step closer to understanding the origins of our cosmos and our own existence within it. In summary, redshift and blueshift are not merely scientific curiosities. They are invaluable tools in our quest to understand the universe. They provide insights into the motion of celestial objects, revealing the dynamic dance of galaxies in the vast cosmic landscape. Thank you for joining us on this cosmic journey.